Hello students, today discussion is alkali metals. Alkali metals comes under S block elements. So this chapter is very important. So in this video, we are going to cover about the general trends like atomic, radii, ionization enthalpy and everything, as well as physical properties of alkali metals and the characteristics of alkali metals, anomalous behavior of lithium, diagonal relationship of lithium with magnesium, chemical properties of alkali metals like how does it react with oxygen, how does it react with water, as well as Downs process for the extraction of sodium. So like the extraction of sodium using electrolysis technique, as well as uses of alkali metals. So let us start the discussion, students. So students, the elements which comes under alkali metals are lithium, sodium, potassium, rubidium, cesium, francium. So students, alkali metals belongs to the first group elements. The first group elements are hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. But listen guys carefully, hydrogen is not an alkali metal. It's a non-metal, but it is placed in the first group. So we don't have the discussion about hydrogen in this chapter. As well as francium. Francium is an alkali metal, but francium is radioactive element. So when the discussion about the behavior, chemical reactivities, we don't discuss about the francium also. So the discussion mainly between lithium to cesium, right students? So look at some of the main points why they are called as alkali metals. All these elements are called as alkali metals. That's a family name of the first group elements. The reason why they are called as alkali metals is because alkali means when a base dissolves in water is called as alkali, which means all these metals, students, they form oxides, the respective oxides, and these oxides are basic in nature, and when these oxides, when they dissolve in water, they produce hydroxides. That means base dissolve in water called as alkali. Alkali metals forms oxides which are basic in nature and they can dissolve in water, producing the respective hydroxides which are the strongest bases. So that's why these family group of elements called as alkali metals. So some of the main points in this alkali metals is mainly associated with lithium, students, because of its least size. So lightest alkali metal is lithium, and except lithium all the other alkali metals are preserved in kerosene, right students? Why in kerosene? Why not in other solvents, like why not in water? Why? Because these alkali metals are highly reactive towards the water. The moment when these alkali metals were associated, when they are dropped into the water, you know, it's like a big explosion. So that's why these alkali metals are stored under kerosene, preserved under kerosene. But why not lithium? So lithium cannot be stored in kerosene. Why? Because it floats on the surface. The reason is lithium being the lightest metal, it floats on the kerosene. So what happens if it floats? We can close the tap, we can still inside the bottle there is some air. Air contains oxygen, air contains water vapor. This lithium may react with that oxygen and water vapor also. So that's why lithium is not stored under kerosene. Then how to store lithium? By coating with paraffin wax. You already know na wax, students, paraffin wax, alkanes, all. So these paraffin wax, when it is coated, so there is no direct contact from the metal surface to the oxygen or the water vapor. So this is one of the reason why lithium cannot be stored under kerosene. Students, clear about the introduction? So let us start the discussion with general electronic configurations. So listen students, all the elements in the same group, they have similar chemical properties. Yes or no? That's why they are called as a family, one family. Alkali metals, they all have basic nature from lithium to cesium. What is the reason behind this similarity? The reason behind this similarity is electronic configuration. Look at these configurations, students. Hydrogen, what is the configuration? 1s1. Lithium, what is the configuration? 1s2, 2s1. Sodium, 1s2, 2s2, 2s6, 3s1. We have to consider only the valency shell configuration because this valency shell configuration is the reason behind all this reactivity. So look at the configurations: 1s1, 2s1, 3s1, 4s1, 5s1, 6s1, 7s1, francium. So all these elements from cesium to from lithium to cesium. So what is the general valency shell configuration, students? S1, 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 S1. Yes or no? That means all they have same kind of configurations or not? So what happens if they have similar valency shell configuration? If they have similar valency shell configuration, they react in a same way. How? If lithium combines with oxygen, it forms the compound Li2O, lithium oxide. If sodium combines with oxygen, it forms sodium oxide, Na2O. If potassium combines with oxygen, it forms K2O. Yes or no? They are combining in the same ratios or not? Their valencies are same. Their combining capacities are same. That is what the similarity, students. And that similarity is because of having similar valency shell configuration. So next we have general trends like first to start with atomic radius or atomic size. Students, the definition of atomic size is the distance from the nucleus to the valency shell is called as atomic size. So trends means, students, what happens group wise, period wise, that is called as a trend for all these elements. So we are talking about alkali metals group, first group elements, right? So let us discuss about the trends for this from this lithium to cesium. So answer, once again I am defining atomic size is the distance from the nucleus to the valency shell is called as atomic size. Which is bigger in size, lithium or cesium? Students, the answer is cesium is bigger in size. Yes or no? Why? Because lithium configuration is 2s1. Its valence electron is located in the second position or not, second shell. Cesium configuration is 6s1. Its valence electron is located in the sixth position. That means the distance from the nucleus to the sixth position increases or not. So top to bottom atomic size increases or decreases? Top to bottom atomic size increases. Students, got the why increases? Why? Because every time a new shell is getting added. Got the clarity, students, about this trend? Atomic radius. Next, ionization enthalpy. First I will define the ionization enthalpy, then we will discuss about the reason and the trends. So ionization enthalpy is the minimum energy required to remove the electron from the valency shell of an isolated gaseous neutral atom is called as ionization enthalpy. In a simple terms, if you want to define, all these are metals, right? Alkali metals. They lose electrons, right? That is what the metallic nature. We'll discuss in the metallic character here, the fourth point. So they lose electrons, yes or no? Like how do they lose electrons? Directly they lose electrons? No. We need to provide some energy. Then only they lose electrons. How much energy they require? How much energy they require? That measuring quantity is ionization enthalpy. For example, let us check the trends. Lithium, cesium. Which can lose electrons easily? Students, answer. First you answer. Lithium and cesium. Which element can easily lose electron? Lithium or cesium? The answer is cesium, not lithium. Why? Because the valence electrons in lithium is closer to the nucleus or not, 2s1 configuration, very closer to the nucleus. If it is closer to the nucleus, it has effective nuclear charge, more effective nuclear charge. Does it easily lose the electrons? No. We need to provide more energy to break that attraction. Yes or no? Got the clarity? Cesium. Cesium valence electron is located in the sixth position, 6s1. So does it get that much of nuclear attraction? No, it has more shielding effect. So the valence electron doesn't get that much of nuclear attraction. With limited energy only, the electron will be lost. Cesium, students, if it is placed in the atmosphere, it ionizes under the sunlight also easily. So cesium is having low ionization energy, lithium having highest ionization energy. No answer the trend, top to bottom. What happens to the ionization enthalpy or ionization energy or ionization potential? All are same. So what happens, students? Top to bottom ionization enthalpy decreases. That means it is easy to remove the electron of cesium than lithium. Students, got the clarity? Atomic size increases, ionization enthalpy decreases. Next, oxidation state. Oxidation state means how many electrons does this alkali metals loses? If they lose, what is the charge that they will get? Like we already discussed in the previous slide, their configurations, their valence shell configurations, right, students? They have how many electrons in their valence shell? 1 electron. Octet rule, according to the octet rule, in order to get 8 electrons in its valence shell, all these alkali metals, they lose only 1 electron. If they lost that 1 electron, what is the charge that they will get? They will get +1 charge. So the oxidation states of all these alkali metals is +1, students. For example, sodium, atomic number 11. Yes or no? Its configuration is 3s1, valence shell configuration. This electron will be lost. Then sodium becomes Na+1, sodium ion. Not only sodium, students, lithium becomes Li plus ion. Potassium becomes K plus ion. Rubidium becomes Rb plus. Cesium becomes Cs plus. So what is the oxidation state of all these alkali metals? +1 state is the oxidation state. Got the clarity, students? Because all depends upon the valency shell configurations. So the next, metallic character. So students, any idea about metallic character? Metallic character is nothing but we can define in two ways. One is by physical properties, other one is by chemical properties. Physical properties means like students, malleability, ductility, sonorous, lustrous nature, that is physical property. But main definition is coming from chemical property, that is ability to lose electrons. An element showing its capacity, willingness or ability to lose electrons is called as electropositive nature. If an element has highest electropositive nature, that is highly metallic. So leave highly or low metallic. First of all, what is metallic? Ability to lose electrons is metallic nature. All these are alkali metals, that's why they are called as metals, yes or no? Then which is more metallic, which is less metallic, we have to discuss here. So what I said, metallic nature means ability to lose electrons. Again, let us compare lithium and cesium. Why? Because lithium top, cesium at the last. Francium is radioactive, leave that. So which is highly metallic, students? Lithium or cesium? Once again I am saying highly metallic means ability to lose, which can able to lose easily. Lithium can lose its electrons easily, or cesium? The answer is cesium. I already have said cesium atomic size is bigger. Its valence electron is far away from the nucleus. It doesn't get that much of nuclear attraction. Yes or no? That's why it has low ionization energy, which can be easily lost. The valence electron can be easily the valence electrons can be easily lost. If the valence electrons can be easily lost, that means its metallic property is high. It is highly metallic. So answer top to bottom. What happens to the metallic nature? Increases or decreases? Top to bottom, metallic nature increases. That means ability to lose electrons increases. Got the clarity, students? So that's what the trends are. So next we have the discussion about reducing properties. So before going to discuss about the reducing properties, we have to define two points here, two definitions, like oxidation, reduction. Oxidation means addition of oxygen, removal of hydrogen. Reduction means removal of oxygen, addition of hydrogen. So what these alkali metals are, what they are showing? Reducing properties. Reducing properties means, students, alkali metals themselves, they undergo oxidation, but they make other compound to undergo reduction. I'll give an example. Sodium plus H2O. What happens, students? What do we get? Sodium hydroxide. Yes or no? That means sodium taking the oxygen from the water molecule or not? Water is undergoing reduction or not? So this metal which makes other compound to undergo reduction, but by itself it undergoes oxidation. So that is what the meaning of reducing property. Reducing property means this metal is not undergoing reduction. This metal makes other compound to undergo reduction. That's why all the alkali metals acts as strong reducing agents. Got the clarity, students, about the reducing property? Next, flame coloration. Flame coloration means, students, first of all, what is the color of all the alkali metals? Not all the alkali metals, students. Almost all the metals are silvery in color except gold and copper. And almost like silver tint or little bit gold tint. That's it. Maximum they're silvery in color only. Take any metal. So alkali metals are also silvery in color. They're soft metals. We'll discuss that point here. So flame coloration means if you try to burn these alkali metals or the salts of these alkali metals, we can expect the following colors. So if you burn the lithium, what is the color, students? Crimson red color. Sodium golden yellow. Potassium lilac, that means like pinkish purple color. Rubidium reddish violet. Cesium sky blue. So why do we have this discussion here? Why? Because in order to identify what type of the metal, burning test is one of the crucial tests to detect the type of metal. If the salt, if it is burning with golden yellow color, so what's the most probable, what's the most chance, what's the metal the particular salt is made up of? Sodium. So for the identification technique, we use this flame coloration. This is also one of the main points, students. Next, photoelectric effect. This is given by Einstein. He got Nobel Prize for explaining this effect. Photoelectric effect means, students, when the metal surface, if it is exposed to the sunlight, the electrons were emitted, and these emitted electrons are called as photoelectrons, and the effect is called as photoelectric effect. So why do we have this discussion here? Why? Because these alkali metals also, when they expose to the sunlight, they emit photoelectrons, except lithium. You have to remember, all the alkali metals show photoelectrons, but except lithium. Why? Because students, lithium size is very, very small, and that's the reason why it has many exceptions. If its size is very small, its effective nuclear charge is also more. Yes, sir, students, does it easily loses electrons? No. From the beginning we are discussing lithium, does it loses its electrons easily? No. So that's why lithium is an exception. So make a note of this point. Next, density. All these alkali metals are soft metals, so they have very, very low density, students. What is density? Mass per volume. Unit volume is called as density. And top to bottom, the density is increases. Why? Because top to bottom, new elements and atomic numbers are increasing, atomic masses are increasing, yes or no? So the density is also increased, but comparatively, alkali metals have low density, students. Next, melting points and boiling points. What are melting points, students? Melting points, boiling points depends upon the forces of attractions between the atoms. So these alkali metals, they have low melting and boiling points, and when from top to bottom, the melting and boiling points will decrease slowly because of this effective nuclear charge, least effective nuclear charge. They exhibit less melting and low melting and boiling points. Next, soft metals, right? All these alkali metals are soft metals, students. There is an exception, that is lithium. That is not very hard, but comparatively it is tough metal. Why? Because the same reason, atomic size is less, it perfectly arranges in its crystal lattice, attractions are more, so it more tightly bound, the metallic bonding, the strength is more, so that's why that makes the lithium tough metal comparatively to the other alkali metals. But all the other alkali metals are soft metals. We can even cut with a knife also, all these alkali metals. Got the clarity about this slide, students? Next, general characteristics of alkali metals. Like if you want to define alkali metals, you can define alkali metals by 3 points. One is, they all have low values of ionization enthalpies. What is low value for ionization enthalpies? They can easily lose electrons with limited energy. Yes sir, exceptions are the lithium. Next, large size. Yes sir, students, top to bottom atomic size is increasing. Left to right, what happens atomic size? Left to right atomic size is decreasing. That means which elements, period wise, which elements have more size, bigger size? Alkali metals. Left to right atomic size is decreasing. That's why large size, as well as low heat of atomization. Low heat of atomization means we discussed in photoelectric effect. With limited heat energy only, they convert it into gaseous atoms. That is called as low heat of atomization. So these are the general points about alkali metals. Next, anomalous properties of lithium. This is the crucial point. These are crucial points which comes under this chapter. Anomalous properties of lithium. Anomalous properties means, students, something which is not following in a way, in an order. That is done by the lithium. Lithium something that is not following. So look at some of the main points where the lithium is showing its anomalous behavior. First, lithium shows its similarity with magnesium. Lithium shows its similarity with magnesium. That differs from the other alkali metals. Why it shows its similarity with magnesium, we'll discuss in the next slide. That is diagonal relationship. So this is one of the difference where other alkali metals are not doing it, not following it. So lithium is hard metal. Yes or no? All the other alkali metals are soft metals. So but lithium is little bit hard. Why it is hard, students? It's small. Its atomic size is small. It fits perfectly in the crystal lattice, as well as because and its nuclear attractions are effective. Electrostatic attractions are also more, intermolecular attractions are also more, so that's why it is a little bit hard, but remaining alkali metals are soft. Lithium directly combines with nitrogen and it forms lithium nitride, while other alkali metals do not form a stable nitride. Yes or no, students? The reason is lithium is a metal. What is the nature of metal? Loses electrons. Nitrogen is a non-metal. What is the nature of non-metal? It will gain electrons, yes or no? But not only gaining electrons, students, non-metals can share electrons also. So this nitrogen belongs to the 15th group. It has higher covalent character, and lithium also, this is also an exception for lithium. Lithium also shows this covalent character. Because of this reason, lithium combines with nitrogen and forms a stable compound, which is a lithium nitride. What is the formula? Lithium valency is 1, Li plus. Nitrogen valency is 3, N minus 3. So what is the formula? Li3N. This is not a pure ionic compound. It has a covalent character. Why lithium shows the covalent character? Why? Because top to bottom ionic nature increases. Yes or no? Which is more ionic, lithium or cesium? Cesium only. We easily lose electrons. Lithium, no, it has the covalent character. That covalent character is called as polarizability. Because of this reason, lithium forms a stable compound with nitrogen, while other metals do not form the stable compounds. Next, lithium directly forms carbide also. Remaining elements do not form carbide directly. So, right, what are carbide, students? C2 minus 2 is carbide. Same, carbon also belongs to the 14th group element. It also has the covalent character. So, this lithium, because of its having the polarizability, it combines with carbide and forms a stable compound, students. Which, while other other alkali metals do not show this carbide formation, the stable carbide formations. So, because of its small size, because of its covalent character. Next, solubility of hydroxides, carbonates, phosphates, fluorides increases down the group. I'll explain this point clearly, listen carefully. So, what is the meaning of solubility? The meaning of solubility is if a salt or a base or anything, if it is dissolved into the water or anything, if it is dissolved into the water, you know, the respective salt solution attracts towards the opposite ions. That means ability to release its ion. That means, for example, water is made up of H2O. Oxygen has a partial negative charge. Hydrogen has a partial positive charge. Yes or no, students? If NaCl is added into the water, NaCl is made up of Na plus ion and Cl minus ion. This Na plus ion attracted towards partial negative charge of oxygen. The Cl minus ion attracted towards partial positive charge of hydrogen. That is what the solubility is. That means opposite ions shows their attractions and they slowly dissolve and they get into the spaces between the water molecules. But this, you know, lithium, for example, take lithium hydroxide, cesium hydroxide, which can dissolve. That means which can easily get into the spaces, lithium hydroxide or cesium hydroxide, which can easily release that OH minus ions, lithium hydroxide or cesium hydroxide. You already know the answer. The answer is cesium hydroxide, students. Why? Because cesium hydroxide atomic size is big, its effective nuclear size is, cesium atomic size is very big, its effective nuclear charge is very less. It cannot bind the opposite ion so tightly. But lithium atomic size is very small, it binds the opposite ion very tightly and it doesn't release very easily, lithium hydroxide. So that's why down the group solubility increases. That means cesium hydroxide can easily release its opposite ion in the solutions. That's why that's the main points in this slide, students. Got the clarity? Next, diagonal relationship of lithium mainly with magnesium. So to start the discussion, I'll explain one general example, students. Listen carefully. Some students are arranged, they sat group wise and row wise. Okay, group wise and row wise. The corner student has 10 rupees. The next person in the group has 11 rupees. The next person has 12 rupees. Next 13, 14, 15. The number of rupees carrying by the each student increases top to bottom. Yes or no? Next, left to right, the number of rupees decreases. Now say, what is the corner one is 10 rupees, right, students? Next one 9 rupees. Next one 8 rupees. Next one 7 rupees. Got the clarity? Top to bottom number of rupees increases for the students, per student. Left to right number of rupees decreases per student. Now, this is the first group. Go to the second group. Second group, first person, how many rupees he has? Second group, first person. Beside beside the student who is having 10 rupees. This person has 9 rupees, yes or no? Next person, bottom. How many rupees? Top to bottom number of rupees increases. How many rupees? 10 rupees. This 10 rupees person is resembling with which person? The corner person or not? That means the first person in the first group, the second person in the second group has same number of rupees or not? Now apply the same concept to the atoms. That means, what is the first person? Lithium. What is the second person in the second group? Magnesium. What do they have common? Here not the rupees, the common thing is atomic size. If atomic size is similar, they show similar properties. Here many students will confuse. Similar properties doesn't mean the same valency. No, they have different valencies only. They show different combinations only by ratio of number of atoms. But the similarity comes Similarity, they show similarity in solubilities, in reactivities. For example, lithium reacts with nitrogen, magnesium also react with nitrogen. Yes or no? And they show the similarity in melting points, boiling points, all these characteristics they show the similarity. So let us look at some of the examples. So lithium is diagonally related with magnesium due to the similar polarizing power. Polarizing power, I told you, it depends upon the atomic size. So it shows covalent character. Magnesium also shows covalent character. Why? Because lithium and magnesium atomic sizes are almost similar. That's why. So electronegativities, charge, everything all are almost same. Lithium reacts with water slowly, but magnesium react with hot water fastly. So they almost show the same kind of reactivities with water also, students. They form the normal oxides. Lithium react with water. What does it form? Li2O. Magnesium react with water. It forms MgO. The formulas are different, but they show the same kind of effectiveness. They show the same kind of reactiveness. Next, right? Both gives hydroxides and they liberate hydrogen. You can look at the formula. Lithium hydroxide is LiOH, magnesium hydroxide is MgOH taken twice, and both releasing hydrogen gas. Lithium and magnesium gives only mono oxides, Li2O, Mg. Why this point is given is the higher members of these groups, they can form superoxides and peroxides also. What are superoxides, peroxides? In the coming slides I will explain. But these lithium and magnesium, they don't give superoxides and peroxides. In general, they give normal oxides only, students. Next, lithium chloride and magnesium chloride are deliquescent in nature. The nature of deliquescency is, students, deliquescent means these salts, when they expose towards the water vapor or water, they attract these water molecules. And they become hydrated salts. For example, lithium chloride. When lithium chloride, when it is in contact with water, it forms hydrated salt. This is called as water of crystallization. That means LiCl.2H2O. Two water molecules attracted towards lithium chloride. Same thing happens with magnesium chloride also. Like MgCl2.8H2. That means 8 water molecules attracted towards magnesium chloride. This is called as water of crystallization. The number of water molecules per unit formula of salt. That nature is called as deliquescency, attraction towards the water molecules. Students, right? Due to the covalent nature, lithium and magnesium halides are soluble in organic solvent. This point also very, very important. I already have told you, lithium having covalent nature, magnesium also showing the same behavior because of its similar size, and because of its similar size, the halides of this lithium and magnesium, they can be soluble in organic solvent. There is one statement called as like dissolves in like. Like dissolves in like. Ionic compounds dissolve in polar solvents. Covalent compounds dissolve in organic solvents. Because of this covalent character, they can dissolve in organic solvents also, like ethanol, ether, kerosene. That is possible, students. All the salts of lithium and magnesium. So these are the main points and the main slide. So diagonal relationship, students. Next, chemical properties of alkali metals. Chemical properties of alkali metals. So we already discussed about the configurations of the alkali metals. They all contains 1 electron. Their valency is 1. So when they react with dihydrogen, students, listen. What's the formula we can expect? Hydrogen, does it loses electrons or gains electrons? Remember, students, when hydrogen reacts with metals, it gains electrons. When hydrogen reacts with non-metals, it loses electrons. That means, students, when hydrogen, when it reacts with metals, it forms hydrides, H minus. If it reacts with non-metals, it forms H plus, which is hydrogen ion. Got the clarity, students? So here, it is reacting with metals. So what is the formula? M plus H minus, that is the ratio. Why? Because alkali metals valency is 1, hydrogen valency is 1, they combine in 1:1 ratio. And these metallic hydrides, when they dissolve in water, they produce the respective hydroxides and they release hydrogen gas. That means these hydrides also act as strong reducing agents or not? You can check, they are taking the oxygen. So these are also strongest reducing agents, metallic hydrides. And what is the valency? What is the oxidation state of hydrogen in metallic hydrides? -1, students, you have to remember that point. Next, reaction with oxides and hydroxides. We already discussed about this point. When metals react with oxygen, what do they form? In general, they form the normal oxides. What is the formula? General formula. M reacts with O2, it forms M2O. Why? Because its valency is 1. Alkali metal valency is 1. They combine into 2:1 ratio, right, students? But in the excess of oxygen, in the excess of air, alkali metals, the higher alkali metals, they can even form peroxides and superoxides also, which is not done by lithium, which is not followed by lithium. So many students have this doubt. They don't have the clarity between oxygen, oxygen gas, oxide, peroxide, superoxide. I'll give the clarity, students, listen. Oxygen symbol is O. It means it is an element. Oxygen gas, it is O2. The formula is O2. It's a molecule. And oxide, it is an ion, O minus 2. Peroxide, it is O2 minus 2. That means there is a bond between oxygen, and each oxygen has -1 charge, together minus 2, O2 minus 2. Superoxide is very rare and highly it is unstable for almost all the compounds. Very rarely it is stable, students. Mostly like potassium superoxide is possible. The formula is KO2. You can see KO2. So O2 minus 1 is called as superoxide, students. So these peroxides and superoxides, lithium doesn't form because of its small size and more polarizing power, but higher members of alkali metals, they form, like from sodium, potassium, rubidium and so on. Right, students, about oxides and hydroxides. Next, reaction with water. So there are so many videos in the YouTube, like when sodium is dropped into the water, what happens? It's a big explosion, yes or no? So what is happening there? When sodium reacts with water, it forms hydroxides and it releases hydrogen gas. It is highly explosive reaction, highly exothermic reaction. As well as you can see here, other compounds containing acidic hydrogen atoms also, it reacts and it releases hydrogen gas. Acidic hydrogen means, students, what are acids? What acids means? The ability to release hydrogen ions, that they are called as acids, yes or no? Acidic hydrogen means, in general, these compounds do not release hydrogen atoms, but we can make them to release that hydrogens. That hydrogen is called as acidic hydrogen. So here, when sodium react with HX, X means halogens, like hydrogen chloride, hydrogen bromide, anything. So it replaces the hydrogen, it forms a respective the salt of halides and they release hydrogen gas. And sodium, when it reacts with ethine, it forms the respective sodium acetylate. That means ethine, alkynes also contains acidic hydrogen. But what is the gas they release? Hydrogen gas will be released, students. Reaction with halogens. Students, alkali metals valency is 1. Halogens valency is also 1. So what is the ratio? What is the formula? In what ratio we can expect the combination? 1:1 ratio, yes or no? That means when the metals react with halogens, they combine in 1:1 ratio. So metal plus X2, like F2, Cl2, Br2, I2, all the non-metal, all the halogens. So what we can expect? NaCl, like LiCl, KCl, NaBr, Ki, potassium hydride. So 1:1 ratio combination. Here the main thing to remember is reactivity of alkali metals and the reactivity of halogens. Top to bottom, reactivity increases or decreases? Many times I repeated this point in this video. Students, answer top to bottom. Reactivity of alkali metals increases or decreases? Reactivity means ability to release its electron, its valence electron. So top to bottom, alkali metals reactivity increases. Cesium can easily lose electron, yes or no? Next, apply the same concept to the halogens. Top to bottom, halogens reactivity increases or decreases? Top to bottom, halogens reactivity decreases. Why? Because halogens, 17th group elements, they do not lose electrons. For them, they gain electrons based on their configuration. So which element can easily gain? Fluorine or iodine? Fluorine. Why? Because it has effective more effective nuclear charge. It can easily attract the incoming electron, yes or no? So alkali metals top to bottom reactivity increases. Halogens top to bottom reactivity decreases, students. This point you have to very clear. So which is more ionic? Students, in halogens, fluorine is more ionic. Fluorine has more electronegative character. So when this lithium combines with chlorine, bromine, iodine, like we already discussed, these salts of the lithium, they have covalent character. They can even dissolve in organic solvents. So that's what the reactivity, students. Reaction of halogens. Next, Downs process for the extraction of sodium. Downs is a scientist name, students. So here we have electrolytic technique to extract the sodium. Look at the whole setup contains the complete steel surrounded by a steel container which is having fire resistant bricks, which is covered by fire resistant bricks. We have a cathode and an anode. What is the charge on cathode? The charge on cathode is negative. The charge on anode is positive. We have graphite anode. By taking the electrolyte of sodium chloride, but it is not pure sodium chloride, students. It's a fused sodium chloride, potassium fluoride or calcium chloride. Fused means molten state. So why all these combinations? We want to we want to prepare, we want to synthesize pure sodium. But why all these combinations? Listen to the point, students. Sodium chloride melting point is very high. Sir, why do we need to melt sodium? Why? Because in order to separate sodium, we have to melt the solid sodium chloride. Yes or no? Under electrolysis technique. If you want to maintain the temperature, its melting point is almost around more than 1000 Kelvin, students. But it is not so easy to maintain that higher temperature throughout the electrolysis process. That's a big problem. And at these temperatures, the pure sodium which is getting liberated, which is produced, that may undergo into vapor state. That is also the second problem. Vapor state means it can convert into gas because of this high temperature. Under these high temperatures, students, sodium and chlorine may be corroded. They undergo corrosion. That means they may react with the surface of all the surroundings. This is the third disadvantages. We can't maintain the temperature. So to lower the temperatures, to lower these melting points, we have to use the impurities like calcium chloride or potassium chloride, so that we can done this electrolysis process. So during electrolysis, what are the reactions we can expect? Sodium chloride will be dissociated into sodium ion, chloride ion. What is sodium ion? Na plus. What is chloride? Cl minus. Now answer, chloride, sodium ion, where it will be deposited? At anode or at cathode? At cathode, students. Why? Because cathode is a negative terminal electrode. Yes or no? These positive ions will be deposited here, and the negative chloride ions will be deposited at anode. And there what happens, students? Na plus ion gains its electron and becomes sodium atom, and chloride ion loses electrons and becomes chlorine radical, and chlorine radical combines to form chlorine gas. You can see there is some dome shaped arrangement here. Why? Because the separated sodium and chlorine at these high temperatures, they may react again. So to separate them, this particular arrangement was given. From here we can collect the chlorine gas, and from here the sodium will be collected into this receiver where it contains kerosene, so that sodium, the synthesized sodium cannot react with the oxygen or the atmosphere gases also. So that's how we can synthesize sodium from this process, students. Almost 99% pure sodium we can synthesize under this Downs process. Here the main points are the reactions which are happening at cathode and the reactions which are happening at anode. Next, the last point, students, uses of alkali metals, right? Definitely we need to discuss about the uses, yes or no? So the first uses, lithium is used as a metal in number of alloys. What are alloys, students? Alloys means when metals or non-metals, when they physically combine together, they form alloy. That combination is called as alloy. Where do we use alloys? Many uses, like statues, coins, all wherever, like utensils, stainless steel, these are all alloys. So here lithium, magnesium alloys also are used in armor plates as well as aerospace, ammunition, and army tanks. It's one of the hardest alloy. So in all these conditions we can use this alloy. Next, lithium carbonate is used in antidepressant drug. That means medicine, students. What medicines are made up of? Compounds only, na? Ultimately organic compounds contains these elements also. Antidepressant drug means, so the drug which can fight the depression, in that we can use lithium carbonate. What's the formula of lithium carbonate? Li2CO3, right? Lithium aluminum hydride, LiAlH4, is a powerful reducing agent. I already explained about reducing agent. What is reducing agent? It makes other compound to undergo reduction, student, by itself, and it undergoes oxidation. So that's the best reducing agent. Sodium as well as sodium amalgams are used as reducing agents in the organic synthesis. That means sodium is a highly reactive metal. It has many uses, many reactions, many organic synthesis we can use sodium. But the problem with sodium is it is explosively react, which we don't want. So to reduce its explosiveness, we can use sodium amalgam. Amalgam means when sodium is mixed with mercury, that is called as sodium amalgam, students. And if you use this sodium amalgam, sodium present in this amalgam will react, but it doesn't react explosively. So that is the use of the sodium, students. So that's all. Almost we covered all the points in this chapter, students. What we covered? General properties, trends, as well as general characteristics and chemical properties of alkali metals, anomalous properties, a diagonal relationship, Downs process, uses of alkali metals, exceptions. So this chapter is very, very important. I hope you got the clarity, students. So please subscribe and follow